Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, just for a second, a massive, violent explosion.
Oh, yeah.
Picture an eruption of just unimaginably dense solar material. I mean, we are talking billions of tons of it, violently severing its connection to the sun.
Right, just tearing away.
Exactly. Tearing away and hurtling through the vacuum of space directly toward Earth.
It's a terrifying thought, honestly.
It really is. And for decades, for you listening right now, you might not realize that our ability to predict exactly when this kind of invisible, highly charged space storm would hit our planet was, well, it was dangerously imprecise.
Dangerously is the right word.
Right, because we knew the storm was coming, but the people in charge of protecting our power grids, our satellite networks, and the astronauts currently in orbit, they were essentially flying blind for most of that storm's journey.
Yeah, operating in the dark when you're dealing with forces on a solar scale. It leaves the people who manage our global infrastructure deeply, deeply uneasy.
I can only imagine.
I mean, imprecision in space weather forecasting isn't just some academic problem. You know? It is a literal existential threat to a technologically dependent society.
And that terrifying imprecision is entirely what we are tackling today, because there's been a massive paradigm shift that just occurred.
It's a huge one.
A recent proof of concept test has completely revolutionized our ability to predict the arrival of these solar storms. It's like a new technological deployment has essentially turned the stadium lights on, illuminating the entire inner solar system.
Yeah, that's exactly what it did.
So for you, the listener, this is really the ultimate story of human ingenuity. We are actively learning to defend our hyper-connected world from the chaotic, invisible, and just incredibly powerful forces of the sun.
And doing a surprisingly good job of it now.
Right. So we are going to explore this critical blind spot that used to paralyze forecasters and the brilliant engineering that finally closed it during this dramatic real-world test in May of 2025.
And what this high-definition view of space means for our fundamental understanding of the galaxy, too.
Exactly. Because before we appreciate the breakthrough, we really have to look at the historical reality, right? Like the mechanics of the threat itself. We are dealing with coronal mass ejections, or CMEs.
Right, CMEs. Because when we observe the sun's corona, we're not looking at a calm atmosphere.
Far from it.
Yeah, it's not peaceful. We are looking at a chaotic, twisted nightmare of magnetic flux ropes.
Like the magnetic fields are constantly tangling and snapping and realigning.
Precisely. And when those massive magnetic structures become too stressed, they undergo what we call magnetic reconnection. They literally snap.
Wow.
And they release a tremendous amount of stored energy. That violent realignment physically ejects a massive cloud of solar material, so plasma and magnetic fields, out into the heliosphere.
And the scale of that ejection is just hard to wrap your head around, honestly. I mean, we are talking about billions of tons of highly charged matter traveling at millions of miles per hour. It's an invisible bullet.
An invisible bullet that is incredibly wide. And if Earth happens to be in the crosshairs of that specific eruption, that CME is going to slam directly into our planet's own protective magnetic field.
The magnetosphere.
Right, the magnetosphere.
Which triggers a geomagnetic storm. And I think a lot of people picture a solar storm like a strong gust of wind blowing against the planet.
Like a hurricane or something.
Right. But the reality of how it impacts our infrastructure on the ground is way more insidious than that.
Oh, absolutely. The mechanism is entirely electromagnetic.
Okay, break that down for us.
Well, when that dense, highly charged plasma cloud hits the magnetosphere, it compresses Earth's magnetic field. And this rapid change in our magnetic environment induces immense electrical currents directly in the ground.
Geomagnetically induced current.
Exactly.
Yeah.
And this is where the vulnerability of our modern power grid becomes terrifyingly clear. Because long-distance power transmission lines, they essentially act as massive antennas.
Wait, really? Antennas?
Yeah, they pick up these induced ground currents. And those transmission lines, they're designed to carry alternating current AC power.
Right.
But the currents induced by a CME are quasi-direct current. DC.
Oh, so that's a huge mismatch.
A catastrophic mismatch. When this massive influx of DC current flows into the high-voltage transformers at substations, it basically pushes the magnetic core of the transformer into full saturation.
So the transformer just can't handle the thermal load at all.
No, it can't. The core overheats,
Yeah.
the paper insulation degrades, the copper melts, and the entire unit can literally catch fire.
Just destroy itself from the inside out.
Yeah. We saw a preview of this back in 1989.
Oh, the Hydro-Quebec event.
Exactly. A moderate geomagnetic storm hit Earth and triggered this cascading failure across the Hydro-Quebec power grid in Canada. Within 92 seconds, 6 million people lost power.
That is staggering.
The transformers were just overwhelmed. And that wasn't even a worst-case scenario storm. It was nothing compared to, like, the Carrington event of 1859.
Right, the one that set telegraph offices on fire.
Yeah. If a severe storm like that hits us today, without warning, we could be looking at widespread, long-lasting blackouts. Because replacing those massive, custom-built high-voltage transformers, it could take months, if not years.
Months without power across entire regions. I mean, which puts the pressure squarely on space weather forecasters. They are literally the only line of defense here.
They really are. The entire strategy for mitigating this kind of catastrophe relies on getting an accurate warning.
Because if an infrastructure manager knows a storm is going to hit at a highly specific time, they can actually do something about it.
Right. They can purposefully take parts of the grid offline, lower the load on vulnerable transformers, or reroute power. They can essentially put the grid into a defensive posture.
But to do that, they need to know exactly when the storm is going to arrive. And that brings us to the historic blind spot.
The dreaded blind spot.
Yeah, because until very recently, forecasters could only continuously track a CME for like 1/5 of its journey from the sun to the Earth.
Just the first 20% of the transit.
20%. For the remaining 4/5 of that millions of miles journey, forecasters had absolutely zero visual data.
Nothing.
The storm just disappeared from their screens. Okay, let's unpack this for the listener. It's basically like watching a pitcher throw a 100-mile-per-hour fastball, right?
Sure.
But the stadium lights completely shut off when the ball is only a few feet out of the pitcher's hand.
That is a perfect way to describe it.
You know the pitch is coming at your head, but you have absolutely no idea when to duck.
Right. Because the older satellite instruments, they were positioned and calibrated to look at the immediate vicinity of the sun. They were great at capturing the initial eruption and, measuring its starting velocity.
But then what happens?
Well, as the plasma cloud expands and moves outward into the broader solar system, it becomes way too diffuse for those specific instruments to resolve against the dark background of space. It essentially just fades into the dark.
So if you can't see the storm for 80% of its journey, how in the world were forecasters predicting its arrival?
Honestly, they were forced to rely on purely kinematic mathematical models.
Just guessing based on math.
Educated guessing, yeah. They would take the data from that first 20% of the journey, so the initial speed and the initial trajectory, feed it into an algorithm, and essentially just extrapolate the rest of the trip.
That seems like an incredibly risky gamble, especially when you're dealing with something as volatile as plasma. I mean, a coronal mass ejection isn't a solid object like a baseball flying through a vacuum.
Oh, far from it. It is a highly dynamic fluid.
Right.
As this massive cloud of plasma travels, it is constantly interacting with the ambient solar wind, the continuous, slow stream of charged particles flowing outward from the sun all the time.
So it's hitting traffic, basically.
Exactly. The CME can plow into slower-moving solar wind and decelerate, or it can be pushed from behind by faster-moving streams and suddenly accelerate. It can expand, twist, deform, based on the magnetic topology of the space it is traveling through.
So the storm is constantly changing its own rules while entirely invisible to the people trying to predict its behavior.
Yeah. And the consequence of trying to mathematically extrapolate the behavior of a chaotic, invisible fluid over millions of miles, it was a massive margin of error.
How massive are we talking?
The previous state-of-the-art methods left forecasters with a 5-hour window of uncertainty regarding when the storm would actually hit Earth's magnetosphere.
5 hours. A 5-hour margin of error. I mean, just put yourself in the control room of a major regional power grid with that information.
It's a nightmare scenario.
The Space Weather Prediction Center calls you up and says a massive transformer-melting geomagnetic storm is coming. But they can only narrow down the impact time to a 5-hour block.
Right, and the economic and social cost of preemptively shutting down a major power grid for 5 solid hours just to be safe, It's staggering.
Yeah, you are disrupting hospitals, emergency services, communications, economic activity across multiple states, maybe entire countries.
But on the flip side, if you decide to wait and keep the power flowing until you see the first signs of the impact on your grid monitors.
You risk thermal runaway.
Exactly. By the time the alarms actually go off, the magnetic flux has already saturated the transformers. The grid is destroyed, and the power is out not for 5 hours, but for 5 months.
It is just an impossible choice built on a totally paralyzing level of uncertainty. We desperately needed a way to track the storm all the way to Earth.
The scientific community needed to illuminate that entire transit corridor. And the solution wasn't just, building a bigger telescope. It required an entirely different architectural approach to observing space.
Enter PUNC, the four-eyed sentinel in orbit.
Yes, PUNCH.
Which stands for Polarimeter to Unify the Corona and Heliosphere. This is a NASA mission that launched in 2025, specifically designed to eliminate that terrifying blind spot.
And the engineering architecture of PUNCH is just a masterclass in addressing the physics of the observation problem.
Okay, how so?
Well, it does not consist of a single, massive, billion-dollar observatory. The system utilizes 4 distinct, relatively small spacecraft operating in concert. And they're all in low Earth orbit.
In low Earth orbit, okay. And their primary capability is providing continuous 3D observations of the inner solar system, right? Capturing a new image of the space between the sun and Earth every 4 minutes.
Every 4 minutes, yeah.
But let's critically examine the engineering logic here for a second. If the goal is to observe the vast expanse of the inner solar system and track a storm originating from the sun, why keep the instruments in low Earth orbit? Wouldn't you want to send the probes further out into deep space, like closer to the actual phenomena you're trying to study?
The intuition to get closer is supernatural, but it completely falls apart when you consider the geometry of a solar storm.
How do you mean?
Well, if you park an observational satellite close to the sun, or even halfway between the Earth and the sun, sure, it gets an incredibly detailed look at the eruption as it passes by. But once that massive cloud of plasma sweeps past the probe
is now looking at the back of it.
Exactly. The probe is now looking at the tail end of the storm. It's completely blind to what the front edge, the part that is actually going to hit Earth, is doing as it continues its journey.
Wow. Okay, that makes total sense. You want to be on the receiving end looking out.
Right. Furthermore, proximity to Earth solves a massive telemetry bottleneck. Space weather forecasting requires real-time, actionable data.
Because a warning 12 hours late isn't a warning.
Exactly. PNCH is generating high-resolution 3D images every 4 minutes. If those spacecraft were millions of miles away in some heliocentric orbit, transmitting that sheer volume of data back to Earth would involve significant signal delay.
And massive power demands for the transmitters, I bet.
Huge power demands. By keeping the 4 spacecraft in low Earth orbit, they can downlink that continuous stream of heavy data almost instantaneously to ground stations. The forecasters get the data the exact moment it is captured.
That is brilliant. But that brings up the other architectural choice. Why 4 spacecraft instead of just one unified camera?
So a single camera, no matter how advanced it is, only captures a flat, 2-dimensional projection of a 3-dimensional event.
Right.
If a massive, complex cloud of plasma is hurtling towards you, a 2D image makes it nearly impossible to accurately judge its true density, its depth, or how its physical shape is contorting.
You completely lose the geometry of the storm.
You lose the geometry, which is where the P's in PMCH comes into play. Polarimetry. These 4 distinct spacecraft are spaced out in their orbit, providing multiple vantage points. As the plasma cloud travels through space, photons from the sun actually bounce off the electrons within the CME.
Oh, Thomson scattering.
Yes, Thomson scattering. When that sunlight scatters off the electrons in the plasma, the light becomes polarized.
Yeah.
So by having 4 distinct spacecraft simultaneously measure the angle and intensity of that polarized scattered light from slightly different angles, the system can literally triangulate the exact position, depth, and structural density of that specific electron cloud.
That is wild. It's basically mimicking human binocular vision, but on a planetary scale. Because our eyes are set slightly apart, our brain can calculate depth. PUNCH is using 4 synthetic eyes spread across orbit to calculate the depth and structure of an invisible plasma cloud in a vacuum.
Exactly. It creates a living, breathing 3D map of the inner solar system, and it updates it every 4 minutes.
The blind spot is physically illuminated.
The data starvation that plagued all those mathematical models is just solved.
I mean, the theory of the engineering is brilliant, but theoretical capability means nothing until it is tested under the chaotic conditions of a real event, right?
Oh, absolutely.
How does a system designed to measure polarized light scattering in a vacuum actually perform when the grid is literally on the line? We have to look at the specific event that proved the architecture works, the May 2025 stress test.
Right. So on May 31st, 2025, a significant coronal mass ejection erupted from the sun. It was a classic fast-moving storm in transit directly toward Earth.
And scientists just seized the opportunity to run a retroactive test. They wanted to prove that feeding this unprecedented stream of 3D data into the prediction models would fundamentally alter the accuracy of the forecast.
Yeah. They took the continuous images from PNCH, again, updating every 4 minutes, and fed them into a highly specialized computer model. And the primary focus of the algorithm was tracking the leading edge of the CME over time.
So the model was continuously calculating and recalculating the storm's speed and its precise geometry as it moved and evolved.
Yes, because speed and geometry are the two critical variables that dictate impact timing. But, tracking the geometry of an explosion in the vacuum of space kind of challenges our terrestrial bias of how fluid dynamics operate.
Wait, yeah, I was thinking about that. Here's where it gets really interesting for me. On Earth, if I watch a storm cloud roll in, I understand its geometry because I can see it interacting with the atmosphere.
Sure.
It has physical boundaries, right? But in the vacuum of space, isn't a solar eruption just a massive, formless cloud of energy uniformly expanding in all directions? Like, how do you define a leading edge on something that has no solid structure?
That is a very common misconception. Space is not empty, and plasma is not just some formless gas.
It's not.
No, plasma is composed of highly charged particles, and therefore its movement is strictly governed by magnetic fields. A coronal mass ejection maintains the twisted magnetic structure of the flex rope that birthed it. It is essentially bound by its own invisible magnetic skeleton.
Oh, wow. So it has a defined structural integrity, even as it expands millions of miles.
Yes, it has distinct shape, varying internal density, and very hard physical boundaries where its internal magnetic field meets the ambient magnetic field of the solar wind.
Okay, that changes everything.
It does. Because PNCH is providing 3D observations via polarimetry, scientists aren't looking at some blurry white blob on a flat screen. They can trace the exact physical boundaries of the plasma density. They can isolate the leading edge, the absolute front wall of the storm's magnetic shock waves that will make first contact with Earth.
The battering ram.
Exactly, the battering ram. And they can watch how that specific leading edge behaves as it crosses the millions of miles of space.
Because the interaction with the ambient solar wind is, like we said, violent and chaotic. As the CME plows forward, parts of the leading edge might encounter a denser stream of slow solar wind and experience massive drag.
Right, while another section of the storm might slip into a fast solar wind stream and suddenly accelerate. The physical shape of the cloud physically warps. It might flatten out on one side or elongate along a specific magnetic field line.
And if the storm flattens out, the leading edge pushes forward and might actually arrive at Earth sooner than if the cloud had stayed completely spherical.
Yes. And if you only had a 2D image, you would completely miss that flattening effect. You would assume the storm is still perfectly round, and your math would drastically miscalculate the arrival time.
But by tracking the 3D geometry every 4 minutes, the algorithm is constantly refining its understanding of exactly what physical shape this object has taken and exactly how fast every distinct part of that shape is moving.
The model is no longer extrapolating blindly. It is literally reacting to the physical reality of the storm in near real time.
So the model tracked the speed and geometry of the May 2025 storm, absorbing this data every 4 minutes. And the numbers that resulted from this tracking, they represent a monumental leap in forecasting capability.
Let's go to paradigm shift.
The timeline of the event demonstrates just how powerful this data stream really is. Get this, 12 hours after the CME left the sun, the model settled on a final prediction. The algorithm stated the storm would arrive at Earth in exactly 8 hours.
Forecasters were suddenly handed an 8-hour definitive warning.
8 hours. But the accuracy of that warning is the true breakthrough here. The predicted arrival time was accurate to within 30 minutes of the storm actually hitting the magnetosphere.
A 30-minute window of uncertainty compared to the historical 5-hour window.
That is a 10-time improvement.
It's unheard of in this field.
But perhaps even more crucial for the people actually running the power grids was a specific metric the model produced, the confidence factor. The algorithm itself was able to reveal when its estimate had mathematically stabilized.
Yes. The stabilization metric is the operational game changer. Craig DeForest, the principal investigator for PNCH at the Southwest Research Institute, he characterized the modeling process as really basic. He compared this leap in forecasting accuracy to moving from a steam engine to a modern internal combustion engine.
I mean, think about that leap from a steam engine to a high-performance engine. And the craziest part is DeForest says the process was actually really basic. So the math didn't drastically change, right? We didn't invent a new type of math to calculate speed and trajectory.
What's fascinating here is that the failure of the old forecasting method was never a failure of the mathematics. The models were fundamentally starved of data. If you feed an algorithm highly incomplete data based on observing only 20% of a journey, the algorithm is forced to produce massive margins of error to account for the unknowns.
Garbage data in, massive uncertainty out.
Exactly. But by simply turning the lights on, by providing a continuous, high-resolution 3D data stream of the entire journey, those exact same basic mathematical models suddenly performed with spectacular pinpoint precision. The equations finally had the real-world variables they needed to solve the problem.
Let's break down why that stabilization metric is so vital for the infrastructure manager sitting in the control room. Because it's one thing to get a prediction, it's another to trust it enough to shut down a regional power grid.
Right. Let's put that manager back in the hot seat on May 31st, 2025. 12 hours after the eruption, the PNCH model processes the latest 4-minute data update and outputs the prediction, impact in exactly 8 hours. But crucially, the model flags that its calculations have stabilized.
Mathematically, what does stabilization indicate?
It indicates a minimization of variance. So over the last several data inputs, the last several 4-minute updates from PNCH, the predicted arrival time has ceased to fluctuate.
Oh, I see.
The algorithm is no longer wildly adjusting its prediction based on new deformations or sudden accelerations in the plasma cloud. The CME's speed and its physical geometry have settled into a predictable, steady state as it crosses that final stretch of space.
The model is effectively saying, I've seen enough of this object's behavior to know exactly what it is going to do.
Yes. It completely removes the anxiety of second-guessing the forecast. The forecaster can call the infrastructure manager and deliver a mathematically confident mandate. You have exactly 8 hours to prepare. The storm will hit at exactly 4:00 p.m., give or take 15 minutes.
And the manager is no longer paralyzed by a 5-hour window of terror. They don't have to risk a massive preemptive shutdown that costs millions of dollars in economic damage.
They can wait, prepare the grid, and implement a hyper-targeted 30-minute protective shutdown precisely when the magnetic shock wave is scheduled to hit.
They save the grid hardware without causing unnecessary societal devastation.
It is the ultimate realization of the mission. The blind spot is eliminated, the grid is protected, and the forecasting capability has matured from rudimentary guesswork into precision operational defense.
The engineering triumph of QNCH is just undeniable. We built a security camera for the inner solar system and secured the power grid, but the story pivots here in a profound way.
It really does.
Because the deployment of this technology did not just solve an operational defense problem, it accidentally unlocked deep astrophysical mysteries. The surveillance data moved beyond simply forecasting space weather.
You know, the pursuit of engineering solutions often yields profound scientific serendipity. When you deploy a highly sensitive 3D observational tool to monitor a specific threat, you invariably capture the intricate hidden mechanics of the environment itself.
And because PUNCH is continuously capturing high-resolution, wide-field imagery of these plasma clouds, astrophysicists started noticing structural anomalies within the coronal mass ejections that directly contradicted the existing theories. The discovery was that these massive clouds of solar material are incredibly clumpy.
Clumpy is the exact term being utilized in the literature, too, despite sounding completely unscientific. But it perfectly describes a profound reality about plasma dynamics in a vacuum.
Because prior to this continuous 3D tracking, the assumption was that a CME started as a violent, structured eruption, but as it traveled millions of miles through the vacuum of space, it just sort of smooths out, right?
Right. It was expected to diffuse into a uniform, homogeneous wave of energy by the time it reached Earth.
Like a ripple on a pond.
Exactly. The expectation was that the fluid dynamics of the plasma would naturally cause the distinct structures to dissipate and blend together, much like a drop of dye slowly dispersing uniformly in a glass of water.
But the PONCH data revealed the exact opposite.
The exact opposite.
The plasma maintains intricate, swirling, chaotic structures. It remains segregated into massive clumps of dense material that continue to evolve, break apart, and merge dynamically all the way across the solar system. The solar storm isn't a smooth, uniform wave. It's a highly turbulent, structured ocean of plasma.
And the physical reason for this clumpiness comes right back to the magnetic fields. The plasma cannot simply disperse freely. It is trapped within localized magnetic pockets.
Wow.
These magnetic fields wrap around the dense clumps of plasma, insulating them and preventing them from smoothing out into the ambient void. The clumps are continually interacting with each other, governed by magnetic tension and pressure, creating a deeply complex internal architecture within the storm.
And the galactic implications of this localized discovery are staggering, because a CME hitting Earth seems like a very localized solar system-specific event. But the material making up that CME is plasma. And plasma is the universal paint.
Oh, absolutely. Over 99% of the visible universe is composed of plasma.
99%?
It is the fundamental fourth state of matter. While we rarely interact with it here on Earth, the cosmos is entirely dictated by its mechanics. The stars are massive spheres of fusing plasma. The vast, seemingly empty spaces between star systems are filled with tenuous interstellar plasma.
Right.
And crucially, the massive sprawling nebulae, the giant clouds of gas and dust where new stars are actually born, those are deeply influenced by the complex dynamics of plasma and magnetic fields.
So understanding how this clumpy solar storm behaves gives astrophysicists direct clues to plasma behavior in distant star-forming regions across the galaxy. But I have to ask, how does a solar storm hitting Earth help us understand the birth of a star millions of light years away?
Well, the major hurdle in astrophysics is one of resolution. We can point powerful observatories like the Hubble or the James Webb Space Telescope at distant star-forming regions like the Orion Nebula or the Pillars of Creation, and we capture breathtaking images of the grand, sweeping structures of those nebulae.
We can see the massive towers of gas spanning light years.
Right, but we cannot see the microphysics. We cannot resolve the tiny, localized interactions of plasma that actually dictate how that vast material begins to clump together and coalesce in the first place.
Oh, I see.
The process of star formation requires material to gather into dense enough pockets that gravity can take over and initiate collapse. The magnetic fields threading through the plasma constantly fight against that gravitational collapse. The interplay between the localized clumps of plasma and the magnetic fields at a small scale, that is the engine of starbirth.
But those regions are simply too far away.
Exactly. The observational resolution completely fails us at the microscale.
It's like looking at a massive, complex painting from a mile away. You can see the broad landscape, the general colors, and the sweeping shapes, but you cannot physically see the individual brushstrokes or how the paint was mixed on the canvas.
That's a great analogy. And the PUNCH mission essentially turned our own solar system into a macroscopic laboratory for plasma physics. Our sun is right next door. When it ejects a coronal mass ejection, it sends a highly detailed, evolving, magnetically confined cloud of plasma right to our doorstep.
And the clumpy structures we observe in the CME, those are the brushstrokes.
They are the brushstrokes.
Yeah.
By utilizing the continuous 3D tracking from PUNCH, astrophysicists can study exactly how these clumps of plasma behave in a vacuum when driven and confined by magnetic fields. They can observe how the clumps merge, how they resist dispersion, and how the magnetic tension dictates their density.
They're literally decoding the fundamental fluid dynamics of magnetized plasma on a small, observable scale.
Yes. It acts as a cosmic Rosetta Stone. Astrophysicists can take the new mathematical rules and fluid dynamic behaviors discovered by watching a solar storm cross our inner solar system, and they can apply those precise rules to their computer models of those distant, unresolvable star-forming nebulae.
It perfectly bridges the gap between the local and the cosmic. The exact same physics governing the clumps in a CME hitting Earth's magnetosphere are the physics dictating how plasma clumps together to seed the gravitational collapse of a new star in a nebula 1,000 light years away.
The behavior is universal. We just finally built a tool sensitive enough to observe it up close.
The interconnectedness of this scientific endeavor is profoundly beautiful. I mean, we initially set out to build a highly specialized security camera. The sole purpose was to protect our power lines and transformers from melting down during a geomagnetic storm.
Very practical terrestrial goals.
Right. And we solved the operational blind spot, reduced a massive 5-hour window of terror down to a calm, manageable 30 minutes, and secured our infrastructure. But in the process of building a tool to see our local environment clearly for the first time, we accidentally procured the mathematical key to understand the birth of stars across the galaxy.
It really demonstrates that our solar system is not just an empty void we have to blindly cross or fearfully monitor. It is a highly dynamic, structured, and observable environment. The more precisely we map and understand the chaotic mechanics in our own backyard, the more deeply we understand the fundamental fabric of the wider universe.
We have journeyed from the visceral anxiety of an invisible threat hurtling toward us in the dark, relying on starved mathematical models, to witnessing the engineering brilliance of 4 small spacecraft constantly measuring scattered light to triangulate the exact geometry of a plasma cloud. We watched the forecasting capability leap from the equivalent of a steam engine to a modern internal combustion engine simply by eliminating the transit corridor. And we end up peering into the chaotic, clumpy building blocks of the cosmos.
It's been an incredible journey.
Which leaves a lingering thought to mull over today. For centuries, humanity looked up at the sun and perceived a static, blinding disk of light. We saw only the surface. Now, we are continuously watching its chaotic, clumpy, magnetic breath travel millions of miles in high-definition 3D. If simply opening our eyes wider, if just turning the lights on and gathering the data that was always there, allowed us to fundamentally revolutionize our defense and uncover the mechanics of starbirth, what other massive, invisible systems operating right now in our solar system are just waiting for us to finally turn the lights on?